think we can start. So we're delighted to have as our final speaker.
So I would like to speak about a lot of conceptual problems that are in applying machine learning to AI research. And I will start by a little flashback once upon a time. So there was about 25 years ago, 1996. At that time, we deployed a machine that would read check amounts in bank processing centers. Or more exactly, a software that went into the machine. And it was a quite complicated thing. So first of all, it was a real application. That thing has processed 1 billion checks per year for 15 years, about 10% of the checks in the US. So that was absolutely real. What's important is not really the machine, but the data. The data we had came specifically from these machines. So it was exactly the right distribution. It was the distribution of the testing data matched the distribution of the field. So we knew exactly that the testing was reliable. The training was more complicated. There was some transfer learning, pre-training, everything was going on there. But the final training data incorporated sufficient data with the right distribution. This is not a general reading machine. It checks. And we could rely on a number of theoretical foundations, like testing data distribution matched the distribution in the field, so the lower Planck numbers applied. And everything that Boris told you about statistical learning theory. We could rely on the training set, testing set paradigm, which has been for decades the main driver of progress in machine learning. And there were some mysteries, like how come we seem able to optimize the absolutely complex function? We didn't know at all. There was some progress. Boris told about these progresses. How come training deep networks seem to elicit useful representation? Where are we doing transfer learning and more things what happened in the time? And we didn't understand, and we still do not understand. Since then, so improvements, deep networks can be thousands of people. And 12 layers of what we do, basically. Recurrent networks work, they didn't work. Transformers seem able to learn complex structures. We cannot decode the structure that they learn, but we can test its existence with prompts, probes. But at that time, we couldn't do that. Maybe the change that's most important is the rebranding. Machine learning has been rebranded as AI. And let's be frank, it's a hostile takeover. A lot of people are not happy about this. And increased ambitions increase difficulties. The increased ambition is that we went from a space where the problems were specific, well-defined distribution, to an open problem. We expect an AI machine to be able to solve a variety of problems, including new ones. Bold claims. Many people claim that LLM-based chatbots can address open domain problems. They're solved that way. And maybe not perfectly today, but progressing at such a fast pace that the outcome is inevitable. Proof? It's true, that's the level of the proof we have today, right? And sometimes it works, let's be frank. So let's look at language model. Starts with Shannon, 48, in the paper, founding paper of information theory. And first is introduce language modeling in the context of communication, telegraphy. In telegraphy, the message you can see distribution, you can code more efficiently. And it's a very clear distribution of telegrams. You can collect telegrams in the values, so let's have them. Then it tries to speak about the distribution of English in general, but it remains very cautious. It says basic English and Finnegan's Wake are very different kinds of English. They follow different statistics. One is quite cautious about this. He stepped forward and he wrote folklore with a good model of the general distribution of English. A machine can accurately reproduce what a human could have said and therefore appears as intelligent as a human. You shouldn't make too much about the appears word, because that was good enough for Turing. Turing claimed that if you appear as intelligent as a human in the Turing test, you are, period. There are other objections to it. The general distribution of English, which mix of sources. Shannon was cautious. Caution is lost. An important function of language is to occasionally express new ideas. This is very important in the story of mankind. The new ideas is probability 0. Numbers So again, Shannon started by asking humans to guess the next letter of short English text, just capitals, no space, space and no punctuation. And he estimated a lower bound on the entropy between 0.6 and 1.4, been refined by Cover and King at 1.25. And a lot of experiments have been made on the same corpus. If you do impulsive, you are 2.21. I learned that from Bob looking. Trigrams, 1.75. Variable length n-grams, 1.46. So the difference between n-grams and intelligence is 0.2 bits per characters. It seems very small. And you can contest these numbers and say maybe it's too simplistic, maybe it doesn't work. But if you try to take, let's say, the kind of, even the best bounds we have functionalization with the right things, and you use all the tricks in the book to make them good, when you reduce the size of the function you want to learn, the number of examples you need increase with the square. So divide the size by n, the number of examples divided by the square. And so, because of this, for a long time, I was first convinced that this could never work. That basically you would need impractically large training set to do anything. And here we are, for using practically large training set. But it's not all of it. So we're optimizing something that doesn't optimize very much. There's not much margin there. Now is a problem. When we sample pieces of text, they don't come from a crowd. That doesn't exist. We always obtain text by following graphs. The internet graph, the citation graph. But suppose you're in a library and you're in the section of books that talk about war, talk about history. You can read one book, and this book tells you to another book, and so on. And you might end up on Dr. Zhivago. And in Dr. Zhivago, you can transition to the areas where they speak about books about law. So what you have is that you don't sample text by drawing from an urn. You sample text with a Markov chain that mixes really badly. So we're a big Silicon Valley company. We can do multi-step sampling, multiple chains. Suddenly, it doesn't matter because the users don't do that. Everyone sees the new distribution. And apparent distribution is different. The true distribution of English doesn't matter. So go back to measuring performance. Average performance of the testing set. If everyone sees a different distribution, you're in trouble. You cannot use the law of large numbers. If you look at the large language model, the benchmark, you see benchmark for reasoning ability and everything. I wouldn't bet my life on that. More exactly, if you take at the time of the first llama, they studied some of the reasoning benchmarks. And they observed that the result depends strongly on how you capitalize the prompt and how you do the punctuation. And they also observed that most papers use the capitalization and punctuation that works best for their model, which is not always the same. So this is the kind of benchmark we have. And now if you run these papers, instead of one benchmark, you have thousands of numbers. They replace quality by quantity. I still wouldn't bet my life on them.
You know, what do you mean everyone sees a different distribution?
Why do I say everyone has a different distribution?
Everyone sees a different distribution.
Because of this, that we sample text with a Markov chain with poor mixing properties. And so maybe you can do this sampling well, multi-sample, multi-step and everything. It doesn't matter because the users don't do that. You sample text with your ways and you don't wait until it mixes. So your distribution is not the same as mine, it's not the same as yours. And this means, this is what's behind having an open problem. If everybody sees a different distribution, everybody has different problems to solve. And that means, for instance, when you speak of a reasoning problem, and we have an idea what is a reasoning problem, well, the details is not exactly the same for you, for me, for you. And it's not certainly not the same for the people who created a little benchmark for LLM. And the number they measure might not work for you, and especially if it depends on the capitalization of the prompt, no, it probably doesn't. So now we have a serious problem because we cannot measure. So at the end of the testing set, training set paradigm, testing is compromised in many ways. So there is everyone sees a different distribution. Test measurements are not really reliable. The real test of the performance of LLM is not the benchmark, it's the Twitter acclamation in this case. the testing set leaks into the training set in ways we cannot characterize. Take, for instance, against a reasoning benchmark problem. You might have the same verbatim in the training set. You don't know because you don't know the training set is too big. But this you can search. You could have in the training set a mild reformulation, the same problem. With all the right templates, and it's already difficult to catch. It might contain a similar reasoning templates applied to different items. So this is very important. It's interesting to know that you can adapt a mild reformulation, or that you can do more and more complex steps to adapt a template from the training set to the real thing. But we don't know how to characterize it. In fact, the best tool we have to scan the training set to look for this kind of things would be an LLM, which we don't know how to measure. So we are a bit of trouble here. So benchmark, what is a number good for? And I claim a number is only as good as the story that explains why it matters. So when we could rely on the law of large numbers, that was the story. In the case of the check reader, we knew that the distribution was the same. We took great pains to make sure that the distribution of testing sets was the same as the one in the field. And the law of large number was enough of a story to justify that our number was meaningful. But in many fields, it's different. Like for instance, we have solid reasons to believe that a microprocessor able to run a test program on the bench will be able to run a different program in the field, provided temperature, clock, power supply, and compliance. We know this because of substantive knowledge about how it works, how it goes. I'm going to skip that one. This is sorry. That's the story of the steam age. That the Stephenson rocket came along before the thermodynamics. But okay, it's a used one. So I'm going to speak about maybe ways to get out. First, relatively small, and then increasingly wide. And at the end, I have a lot of examples because there's a point where I don't understand very well. And I hope that we will need to discuss. So there's something that I call compositionality, and maybe it's like the group points that were discussed earlier. Going to table. So let's take an example, thought experiment, expressing a new idea. So we already established there are plenty of sources of, let's say, English. And suppose you train a machine with a perfect statistical model of English using an adequately weighted mixture of all English written or spoken up to 2024. Adequately weighted is the threat. It's what they do. They weight things, they put a little bit of Wikipedia, this, I'm going to increase that one, I'm going to decrease that one. And imagine a text that describes a novel physics theory yet unknown to mankind. Well, the model gives infinitesimal probability of such a text, like the Shakespeare monkeys. You know? Infinitesimal means so small that there is absolutely no support for it in the data. This is a very distant tail of the distribution, far from infinite examples. Yet, giving a leading place of this text, the model can generate completions. So what can we expect? So what would we expect from a human? We expect that a human will give structurally correct sentence, meaningful arguments, but most likely fiction, because the human cannot know facts that are yet unknown to mankind. What can we expect on the sole basis of a statistical model argument? Well, the conditional probability is the ratio of the two probability is 0 or 0, it's missing. What do we get in practice? Closer to 1 or closer to 2? You know?
It seems like a well-defined question.
Well, it's not a well-defined question because in practice you cannot do this text.
Two is.
Yes, but if in practice you try to go in the distant tail of the model.
Two is very poor.
Yes, if you rely only on the statistical model argument, you get nothing. But from a human, you would expect something else, right? And if you try a model conversation with a machine, here's a story. Jacques calls his model to tell you about his discussion with Lucy. Rewrite in the past tense, no problem. Add that the topic was Lucy's jacket, no problem. Change this, change that, put it in German, change it, add something else. Step by step, you can make the story drift to the long tail. It's still going to make sense. So basically what's happening is that what the model has learned is not really a statistical model of English. It has learned how to manipulate sentences or how to connect sentences that are connected by simple manipulations. And say that. And basically I've learned what I call the compositional properties of language. And this is what allows us, humans or machines, to create text in the distant tail with no support from the data that's still meaningful, even though it might not be true. And we have unsuccessfully tried to learn such models for decades. And transformers seem to be achieved the feat, and we're barely starting to understand why. By barely, I mean really barely. I'm going to give a hint for this.
So what do you mean by compositional here? Give like a more definition.
Well, the definition is precise. I'm going to get a bit more precise later, but it demands to be more precise. But what you see is that, well, I'm going to talk about this later. In 1968, Zelig Harris wrote a little book called The Mathematical Theory of Language, and the defined operator grammars, where it says, I can describe English by defining a couple basic forms and transform some sentences that generate a set of language that could be close to English. And when you push this idea, you get the idea that you can manipulate sentences, or that two sentences can be related but differ only by one thing, which could be a complement, double extra words, or tense, or the name of the people who are inside. And this kind of proximity between sentences is something that these models do sufficiently well that after a little bit of instruction training, you can even ask the model to make changes, and it's going to make them very reliable. And this is not something like reasoning, which works X% of the time. This works all the time. You can try it anytime you want. This is something that these models do extremely well, and that we don't understand. So anyway, we're having two perspectives. The classic one perspective is that every piece of text follows a conditional distribution given the preceding text. We construct a general statistical language by minimizing a token prediction cost, like an entropy. We might have to cook a good data set by finding the right mix of sources, and we hope that the model will discover representation that will give us good prediction with the data. Another way to look at it is say, every piece of text follows its own distribution, conditioned factors that we may or may not know. Get a piece of text, it's going to be different. But they have a common structure that we should discover. Common structure has to be defined. If we find the right structure, the model will quickly adapt to new text and predict the remaining text more accurately. And this can also result from minimizing the token prediction cost. There may be better ways, but it depends on how the system is set up. What I didn't say, that this is an effect of scale. And these, I think, are evidence for it. So here's another example. You have a planet, you have 3 moons around the planet. And astronomers, they're prehistoric astronomers, they don't know anything, but they want to predict where the moons are going to be. The first one says, well, I'm going to take a table, log the position of my 3 planets. And whenever I see, so my 3 moons, whenever I see my 3 moons in the position that I've logged, I can read following positions. The other one says, well, no, I'm going to make 3 tables, 1 for each moon. Do the same for each moon, and then together. So the first one has to see a full period of the combination of 3 moons, which, if it's integer, would be a least common multiple. While the second one needs only to see the period of the longest moon. Right? So can we do that in the network? So we have an architecture to do that. What's interesting, it has 27 complex parameters of 54 reals. It's very small. And when we train it, we draw 3 periods. And we generate moon position independent, no interaction, the moons don't collide, nothing like that. And the cost is measured and summed at every position in the frame sequence. So the cost is this area under the curve here. Cost, you have the sequence. On the right, you have a big table. So it can tell you something. On the left, there is no table, prediction is bad. So when you minimize this, I claim that you're pushing here, and you're asking the memories to learn quickly. So the idea is that you want to set up your memories, your tables, basically, so that you learn as quickly as possible. You will, if the data supports it, you will prefer to be astronomer B than astronomer A. And when you try, it works. So if you only have one memory head, so one table, the black things are the periods of each moon. The red one is the combined one. You have to see the combined period to be able to predict. If you have three heads, during the learning process, the machine will learn to separate the moons, set them to different tables, look into different tables and recombine. And after each period, you get something. And here it's interesting, because here you see moon configurations you haven't seen before. But because you've seen each moon in that position, you can make a prediction and it's correct. So there is a kind of extrapolation going on. So why this is connected to language? Suppose you want to change a sentence or something else. You have to consider the tense of the sentence. Something you can change pretty much independently from the rest, right? And you have the name of the people involved in the sentence, or you have a position. And the first thing to do to learn to do these things is to identify what are these atomic elements. You can change pretty much independently from the rest. And a system like this does it. The key here is that the cost function is not goodness of fit on the global distribution. It's more like adapting quickly to a new distribution, which can be close. It's up to a clipping, yet you need to clip the cost to do that. So you can see a slight shift in the way these things work. So now I'm intending to be.
Might you also not have to change your cost function, which is to align the fact that you keep training more quickly?
But there is something that helps here, is that this thing where the horizontal and the vertical slices are going to, it works well when it's bounded. So clipping a little bit the cost will help you making sure that your optimization try to minimize the time that each table needs.
I was trying to, so at least in our personal discussions, you said that there might be a term in the cost function to encourage this compositionality. So is that part of what you're saying now?
Well, in this kind of architecture, with this kind of training process, and assuming that the cost function is clipped, depends how it's set up, you can see that the training process will cause the memories, the tables, to try to model the part of the phenomenon as quickly as possible.
Yeah. Well,
And which in turn will cause the network to organize the prediction in independent components.
that's just the nature of training. Two models and it tries to learn from both.
I'm sure I understand, sorry.
So there's model A and model B. And,
Oh, model A and model B.
Model B is learning more quickly, and so.
Yes, maybe, but it's also shown in the fact that you have costs of one. Okay, it's a detail really. So I'm going to broaden the perspective. At some point, I was very frustrated by what I was seeing. And I was frustrated by the idea that everybody seemed to reason about AI by thinking about science fiction. So I decided to look into something else. So with Bernard Schokop, we decided to look into Borges. And Borges is this nice novel, The Garden of Forking Paths. It's a complicated thing, but in the middle, there is this very kind of special kind of a book. It's so when you have a story, there can possible outcomes. Fang can kill the intruder can kill Fang, both can be saved, both can die. In this work, all possible solutions occur, each one being the point of departure for other bifurcations. So let's take set of all the text that makes sense, which is a sentence, to be defined precisely already. Not instruction, just a set. And here is a perfect language model. As a tape, as words printed on the tape, find an occurrence of this in the set, take the next word, output it. And the interesting thing is that each word added on this tape narrows the subset of possible continuation. Each addition constrains the story that's on the tape, the characters, their role, their ID, their feature. And of course, you cannot represent such a set. And again, in Borges, he said writing long books is laborious. A better procedure is to pretend that these books already exist and to offer a commentary. which to me is interesting because we cannot write pi, but we write a lot about pi. So it's a perfectly valid way to do it. And I come to the structuralist. Zelig Harris, I call him the last structuralist, at least at the beginning of his life. And the structural linguistic is based on two ideas. Each language is a set of discourses, the garden. It's shaped with regular structures that can be discovered from examples, which is something as a machine learner like. Later, linguistic evolved by strictly separating grammar and semantics, which makes sense in English, maybe less in Chinese. There was great advance in formal grammar theory. It was absolutely wonderful to create compilers. But the LLMs is not one of these advances, very clearly. And in this book of 68, Harris defined the garden of all text as a set of discourse described by basic forms and successive transformations. That's called the operator grammar. And I claim it's maybe a group of it because these transformations, they are associative. You can reverse them, maybe in the discussion about the details. And you can have a neutral, which is not transformed, but they're not complete. An important thing is that transformation are not just syntactic, they impede on semantics. I change a place, I change the tense, I change the semantics. But if you have something like this, you can complete or chat. You have a premise, a question. You do some transform to match the beginning of the template. Then you take the end of the template, you do the reverse transform, and you get a continuation. Maybe you can do that on several levels. At any instant, our machine is about to continue a story that's constrained by the narrative demands. There is no truth, no intention there, just the narrative necessity. And the ability to recognize the demands of text, kind of knowledge, it's not the same as the truth. What is true in the world of the story is not true in our world. And when you print new words, well, the machine borrows facts from the training data, which are not always true, completes them, getting something that's not always false, and you hallucinate and plenty of things of that kind, and that's normal. This is to be expected. So this is fiction. In language, you wonder when there was truth in fiction. There was Lewis was a professor in Princeton in the 70s. And Sherlock Holmes lives on 221 Baker Street. True or false? Well, it doesn't exist, so it must be false. It's better than say that he lives in Italy. 215 to 229 used to be assigned to a bank, which is now owned by a Russian oligarch under sanction. But now there is a 221B, which is the Sherlock Holmes Museum. There's a place of 237. So true or false? And this way was to involve multiple words. In the fictional world of Sherlock Holmes lived on 221 Baker Street, which is correct. And things get a lot more interesting when you write assertions that span multiple words. Again, Lewis examples. If kangaroos had no tails, they would talk over them, which means that in words that resemble are except for this fact, this would happen. It's a counterfactual, and it's the beginning of modern logic. Beginning of modern logic, meaning, maybe I'm not going to insist on this, that it doesn't fit very well in Boolean logic. And that if you have sentences that are counterfactuals, you don't want all of them to be true. But if you model them by implications, they should all be true, so you have to do something. So let's define the fiction machine. A machine that prints fiction of intent, nothing else. And I claim that our LLMs are approximation of a fiction machine, and that people want to sell them as a fast-growing AI, but yeah, it could lead somewhere, that's another talk. Now the question is, can we do interesting world modeling with fiction? And here I have to put this because there are many mathematicians here. There was Winston, who was a computer scientist in MIT at the time of Minsky. And at the end of his life, he claimed that, well, there were smart mathematicians, but they thought reasoning is the key, not the byproduct. For him, storytelling was the key, and reasoning a byproduct of storytelling. How does it hold? It's true. Well, first of all, when we retell factual events, we cannot account for all the alternative timelines. For instance, an example like this, understanding the history of a battle. Suppose you have a kind of textual log, everything that happened in the battle. At that time, that day, that fact. That time, that day, that fact. You know about the battle, but you haven't understood anything. To understand, you need to be able to say, oh, if this had been different, the story would have evolved this way. If the general had made another decision, the story would have evolved another way. So, in order to understand the true story, you must be able to formulate stories that aren't true. So, often using. And the thing I'm using, the fiction machine can generate these narrations. Perfect fiction machine. Don't have a perfect one. And hallucinations are useful. So let's take another idealized machine, the truth machine. Tell us whether a piece of text is something that is true in our world. And look in the distant tail, not in Wikipedia, the distant tail, in the context. So with the fiction machine, we have all this compositional structure of language that allows us to make legal, meaningful sentences in the distant tail. Well, the truth is not so simple, because when you start changing things, it might not be true always. But this deserves to be looked more closely. But the interesting thing is that this is not far what people do. They train a language model first as a language prediction. There is a lot of fine-tuning where they fine-tune the language model to work as a chatbot and match what are perceived user preferences, which might be about the truth in our world. But the distant tail is going to be much harder here. So, example number one. Now, at this point, I only have examples, and I hope that we want to discuss the examples. That's the laundry. It was ChatGPT for a couple of months ago. Now it's changed because they, whenever there is a problem like this, they keep training, so it's a moving target. Suppose it takes 3 hours to dry a shirt, 5 hours to dry a pair of pants. How long would it take to dry 2 shirts and 4 pairs of pants? And says to determine the total drying time, well, for 2 shirts, 2 times 3 hours, 6 hours, 4 pairs of pants, 4 times 5 hours, 10 hours. Total, 6 hours. I call this a successful application of the wrong reasoning template. But if you replace dry by iron, then it works. And the question doesn't specify the size of the drying line, because if it's small, you can dry only 1 piece of clothes at the same time. It will be right. So you have something where you have incomplete specification that leads to multiple solutions, but the solution that the machine gives is the wrong one for most. Another example, robbery. Some text transformation can lead to meaningful sentences that are no longer true. The bank robbers left with a powerful yellow car. They left with a powerful red car. This is still meaningful. It's less useful to the police. Minutes later, the traffic police stopped the speeding yellow car and caught the robbers by pure chance. So if you have a more complicated story, then suddenly changing red doesn't work, and you change red as well. So you have some constraints. The narrative necessity creates constraints that might not allow you in all cases changes that are that lead to something that is important. Mathematics. Some text transformations are designed to transform true statements into true statements. And here is one that I think from Bottou. And I don't understand. Sometimes record comes at the expense of human understandability. So an interesting thing is true in which words? All words. In the words of mathematics. How do we map what we see in our world to mathematical objects? Something a little tricky there. And what you see is a lot of hybrids, like physicists combine textual stories and mathematical prescriptions. That's Newton's first principles. That is actually that you can make an object deviate from its initial trajectory if you apply a force. You can compute the revised trajectory with an ODE, essentially. And note that there is a causal implication, which was not obvious to express with just. But there is also something about the mapping of what we see in our world to mathematical objects that can be subjected to mathematical treatment. There is something happening here. So if I go to theories and experiments, the truth machine supervised training with label examples is not going to fly. In the distant tail, there is no support for the truth whatsoever. But we can take a two-tiered approach. First, use language to construct stories, theories that may or may not map the world, and try to validate them. So, weather. The weather as an expression of the moods of the gods. There is thunder because Zeus is angry. There is a small ray of sun because Hera just arrived. Zeus anger will subside and fair weather will return. Of course, you can't do that very much because the moods of the gods are unpredictable. Okay, that's the theory of weather. Here's another one. The weather as a dynamical system obeying some flavor of Navier-Stokes, maybe with water phase change and other refinements. Finite element simulation tells us a white thunderstorm will subside and the fair weather will return. Of course, there is only so much you can predict because it's chaotic. So this works orders of magnitude better than the other one. But there's also a limit which is of the same nature. So interesting. And we have another one, which is the weather according to the TV angle. A mass of warm air coming from the south met a mass of cold air from Canada. They got a big fight and big thunderstorm. Fair weather will return when the system moves west. And you can predict as long as you see it on the radar map. So you could say that this comes from the Navier-Stokes because they got the result. But you look at the radar map and you can acquire as a skill a certain level of prediction, which has nothing to do with Navier-Stokes, but which would be far better than what you're going to do with mythology, right? So how do we decide which mythology offers the best way to reason about the weather for our world, imaginary one? Well, each mythology is a theory. Facts observed in our world can invalidate mythology, so let us decide that some are better than others. And you start thinking and you start doing science. So the idea there that maybe you do science because in language you can model this entail with transformations. In the real world, it's more complicated. And we have mathematics as a kind of bridge where you can do transformation of language and maintain truth. So they act as a shortcut. And I really want to understand this. That's why I'm here. So if I conclude, the recent ML or AI engineering achievements inspire huge expectations, massive investment. At the same time, they undermine both the theoretical and empirical foundations of machine learning. So we urgently need a conceptual breakthrough.